Welcome to Lab Math Lesson 1, Basic Skills, Factors, and Conversions. So a few lab math rules that will apply to the duration of the course. All answers must be rounded to the appropriate sensitivity, and answers must be neat and legible. Answers must include units where appropriate. Please make sure to place a 0 before the decimal point. Questions that ask how require a narrative. Don't give just a numerical answer. Remember that the final answer will be graded, so there's no partial credit. And all graded work is to be done independently. A few definitions. Serum is the fluid remaining after red blood cells are removed from the clotted blood sample. So clotting factors are present in the tube, and like you see there in the serum separator tube at the top of the screen, and the serum is on top of that clot. Plasma is fluid remaining after the red blood cells are removed from anticoagulated blood. For example, the plasma is what is in that EDTA tube on the bottom half of the screen. Accuracy is how close a result is to the true value. And precision is how close multiple results are to each other. Lab results should always be precise and accurate. If they're accurate without a repeatable result, then we won't consistently be correct. Or if they're not precise, or if they are precise and not accurate, then although they are repeatable, they're not the right result. The demonstration in the pictures makes it a little easier to understand. And what we always aim for is the precise, accurate results. Sensitivity is the ability of a method to detect the smallest amount of a substance. And specificity is the ability of a method to detect only what you're assaying so that there's minimal interference. A reference range or a reference interval are the values from a reference population used for comparison of results. It's where we get the normal range. Ratios and proportions. So a different quantity but the same concentration, 1-to-1 is an equal relationship. And a 1-to-2 tells us that one value is twice that of another. For example, if you have 2/4, it is equal to x, which is our unknown, over 8. So how would we get the result of x? If you cross multiply to get the 2 times x equaling 4 times x, you will get that 16 equals 4x. If you multiply both sides by 1/4 or divide both sides by 4, you get that x is 16 divided by 4, and x equals 4. So the answer would be the fraction 2/4 equals 4/8. Percentage and decimal form. So the percentage is based on 100, and it is essentially the ratio of a quantity of a substance per 100 total parts. For example, a 10% bleach solution would be 10 parts bleach to 100 total parts. It can also be written as 10 over 100 or as the decimal form of 0.10. In lab math, again, always put a 0 in front of the decimal point. You want to draw attention to the decimal point, and 0.5 milligrams is much different than 5 milligrams. So it's very important that we're very specific about our decimals. A couple of rounding rules. If a value is less than 5, you leave it as it is. And if a value is greater than 5, we increase it by 1. If a value is 5 and the preceding number is even, we're going to leave it alone. If the preceding number is odd, we're going to increase it by 1. There's a few examples rounding there to the 10. Round to the method's analytical sensitivity as expressed by the reference range. For example, a glucose reference range would be 65 to 110 milligrams per deciliter. If you had received a result of 70.2, then you would report out 70 because the reference interval was in whole numbers. Also, we're going to round off to the nearest neighbor. So if you're rounding to the 100th, then you would round there. 1.74 would be your result. If you're rounding to the 10th, then 1.8. Also make sure to remember that you round off the results at the final step. So if you have a multi-step problem, you're going to wait to round till the end. The metric system is based on a power of 10, and there's the units for clinical use: kilogram, deciliter, milligram, microgram, picogram, femtogram, or femtoliter. With these units, you want to clearly mark the tail on the microliter to avoid any confusion, and make sure that the M of the milliliter is clear to distinguish from the micro. Of course, Yocto is 10 to the negative 24. There's just another chart of the factors and the prefixes and abbreviations for each one. A couple of examples of non-metric to metric conversion. So let's convert 5 foot 3 inches to centimeters. So we know a couple of conversion factors. The 1 inch is 2.54 centimeters. So 5 foot 3 inches would equal 60 inches, and then 63 inches, and 63 inches times 2.54 is going to yield 160 centimeters. So how many millimeters would that be? If an inch is 10 millimeters and 160 centimeters, you multiply that by 10 millimeters per centimeter, and it equals 1,600 millimeters. I just realized there's an error on this slide. So this is supposed to read 1 centimeter is 10 millimeters. And then it would make sense. The 160 centimeters times 10 is 1,600 millimeters. For weight conversion, 1 kilogram is 2.2 pounds. And then temperature, all 3 of these are used in the laboratory at different times: Celsius, Fahrenheit, and Kelvin. Remember, when you're using Kelvin, the lowercase k and no degree sign. To convert Celsius to Fahrenheit, we're going to multiply by 1.8 and add 32. For Fahrenheit to centigrade, we're going to subtract 32 and multiply by 0.556. And then if you're going to convert Fahrenheit to Kelvin, you first convert the Fahrenheit to Celsius and then add 273. So different factors. When you have to correct for sample volume, you divide by what was used and multiply by what should have been used. In this example, we have a glucose procedure that requires 2.0 milliliters of serum, but we only have 0.5 milliliters of serum. We know that it's okay to run on 0.5 because we've done validation studies down to 0.1 milliliter, and you perform the procedure and obtain a result of 25 milligrams per deciliter. What would we report out? So here, if we know that our result was 25 milligrams per deciliter with 0.5 mLs of serum, and we would normally have 2.0 mLs of serum, the X would be the result that we're looking for. So if we cross multiply 25 times 2 and then divide by 0.5, you're going to get X is equal to 25 times 4, or 100 milligrams per deciliter. Oh, sorry, I went too far. So this is just an example of compounds. So when you have a concentration of the same, they're both milligrams to milligrams, we're going to calculate a factor. So given 25 milligrams of chloride, what would be the equivalent concentration of sodium chloride? So if we know the molecular weight of chloride and we know the molecular weight of sodium chloride, we're going to calculate a factor of 58 divided by 35 is 1.66. So if we know we have 25 milligrams of chloride, the equivalent concentration will be multiplied by 1.66 to give us 42 milligrams of sodium chloride. And that's all for this lesson. If you have any questions or comments or requests, please contact me on the chat section in Sakai. Thank you for attending.